I want to first thank all the people I've been working with, some of whom are on this slide. There are some of whom who are not, and I apologize in advance. The ones in red are my students, and many of them are here at this workshop. So please go and say hi to them. Merrick will be speaking, I believe it's tomorrow. And An and Yiting both have posters here. Hung Yue will be helping with the Warvara section. Okay, so we've heard a lot of wonderful things about Gaia. There it is, close up. And we've heard this in the last talk, some of the wonderful things that we're starting to get with Gaia DR3, with the orbits and the accelerations, the first planets directly from Gaia. It's limited as of yet, and what I want to tell you about is what we can do beyond that. Taking advantage of the fact that Hipparchus measured 100,000 positions in proper motions almost 30 years ago. And so this is going to leverage that baseline of 30 years between Hipparchus and Gaia to see what we can get. I want to say at the outset that this talk is going to contain almost no results. The reason is because those are going to be in two other talks, and I don't want to repeat all of that. So Pierre Carvella will be speaking tomorrow, as will Merrick Brandt. Both of them will have lots of results in their talks, and so the results part of that is basically deferred. So I'll be talking more about the background, the methods, the caveats, what you have to watch out for, which will also be relevant to the hands-on session, and the scientific payoff, again, will be deferred by, I guess, one day. So I'll start out with the pop quiz here. How many proper motion measurements are shown on this plot? So if you want, you can hold up your hands with a number. I see 2s and I see 3s. Bit of a mix. I drew 2 here, but in fact, there are 3. It's not really a proper motion, as in it's not an instantaneous velocity, but then again, none of these are. Gaia is not measuring RVs. RVs are measuring velocities. Gaia is measuring positions, and it's fitting for a velocity. So there are 3 on here. And that long-term proper motion, a change in position divided by the time baseline, that denominator is around 25 years. 24.25 was the nominal number between the catalog epoch of Hipparchus and the catalog epoch of Gaia DR2. With the catalog epoch of DR3, it's now 25.75, but that's not a magic number. That's a number that was chosen for convenience by the team to be representative. In fact, it does vary star by star. So Gaia is much better than Hipparchus, but the fact that there is that 25 years on the denominator counts for a lot. If your position measurement isn't so good, then getting to divide it by 25 years can give you still a very good velocity, or in this case, a proper motion. And so for many of these stars, I think it's around half now with Gaia eDR3. It was almost all of them with DR2. This long-term proper motion is the most precise, and it is limited by the Hipparchus positional uncertainty. It's a change in position divided by a change in time. And the remarkable thing that I hadn't appreciated when I first got into this myself is that this change in proper motion potentially probes an acceleration in an inertial reference frame, because Gaia is tied to a reference frame that is, for all intents and purposes, fixed. It's linked to the quasars that are so distant that they're basically not moving. Incredibly, this is these kinds of motion across the sky by combining the whole catalog, you can start to see in Gaia. But for an individual star, basically we have a fixed celestial reference system. It defines an inertial reference frame. And so we're probing acceleration in an inertial reference frame. And that means you can go back to Newton's law of gravity, and it applies. Acceleration is gm over r squared. That's it. So that's what we want to be able to take advantage of here. We do need to keep in mind that these proper motions are not instantaneous velocities the way they would be for radial velocity, where you're measuring a Doppler shift. They are fits to a bunch of positions. This is a cartoon that Merrick made showing kind of how this would work. where if you measure a bunch of positions indicated by those blue ellipses, then you might fit, in this case, the green diamond for the point at its reference position, and then that big black arrow for its motion. So it's fitting a position and a motion to a bunch of positions. That's what you're getting out. And that's going to have important consequences. One of which is that if you have a short orbital period, such that those measurements wrap all the way around the orbit, you're not going to be able to get a meaningful velocity out of it. And so in order for this kind of a game to work and for this motion to make sense, you need the motion within Gaia or within Hipparcos to be something kind of sort of like a straight line. If it's not, if it shows a whole lot of curvature, then it really falls into the non-single star solutions that Alessandro was talking about just a few minutes ago. Also keep in mind that these accelerations, they're in an inertial reference frame, but they're in angular coordinates. So we use these astronomer units, milliarc seconds. So this angular acceleration, you need to translate to a physical acceleration in order to get a mass or physical understanding of what's going on. The closer you put something, the smaller the physical acceleration you need for a given angular acceleration. So your acceleration in physical units, I put AU per year squared to make the units work out here, is your acceleration in angular units times the distance. The farther away you are, the larger physical acceleration you're getting for the same angular acceleration. And because you are fitting a line, this only works well if your orbital period is reasonably long. I put greater than about 5 years, but that's a very, very twiddly statement. Okay, just to give you a few more numbers to have in the back of your mind, because I find these useful. I continually forget them and then have to work them out again. So this reflects, broadly speaking, the kinds of precisions we're talking about now. We can kind of see a change of about a tenth, a bit better than a tenth of a milliarc second per year between the long-term proper motion at delta x over delta t and the motion as measured by Gaia. The long-term proper motion is at some epoch in the middle, you can think of it. And so it's not 25 years between those two proper motions. It's kind of half of that because you have something kind of spanning the whole thing. You can count it as being in the middle. And so the accelerations that we're sensitive to are something like 0.01 milliarc seconds per year squared. A bit better than that for many stars. And the acceleration that this gives you in physical units depends on how far away you are. So I put it there for 40 parsecs, but if you're closer, that number goes down. If you're farther away, that number goes up. It's a couple meters per second per year. And if you're coming from the radial velocity world, that's not so far off from the sensitivity of radial velocity surveys to trends. So the long-term radial velocity precision is now not so different from the long-term precision astrometrically across the sky, which is kind of astonishing, given how small these angles are. We speak in units of milliarc seconds, but if you were to convert these to radians, you're talking 10 to the minus 10 or something. So it's absolutely astonishing. It'd be like the width of a hair or a speck of dust as seen from where I drove from this morning in Santa Barbara. Here I'm giving you a rough idea of the masses that you would get corresponding to this acceleration. And then another important thing is that the acceleration, Newton says it's m over r squared. And so that's a quantity that you can hope to probe just with astrometry from these accelerations is m over r squared. So that's why that r squared shows up on the right-hand side, given that I've solved for m on the left-hand side. I can have a small mass companion nearby, or I can have a more massive companion farther away. And for example, this would correspond to a 1 Jupiter mass companion at 5 AU, or 100 Jupiter mass companion, which is a low mass star, 10 times farther away, 50 AU. So those are rough numbers to have in mind. We're sensitive to Jupiter-ish things, potentially, at Jupiter-ish orbits around stars within around 40 parsecs. If we also have some other data, then we get a remarkable little combination that we can do, a little trick we can play. because this is an acceleration in an inertial reference frame, Guy is measuring one projection, one component of that, perpendicular to the line of sight. And so all I've written is Newton's law of gravitation on the top, but I put in an angle where that theta is the angle with the line of sight. For the radial velocity, you're measuring the other component, and radial velocity people need to correct for the Earth's motion around the sun. When they do that, they essentially put the radial velocity again into an inertial reference frame. And so you get to write down the same thing. It's the other component of the acceleration. So if you happen to have both of these, you get a 3D acceleration in an inertial reference frame, which is kind of cool. If you also have a measurement of how widely separated they are, for example, you have high contrast imaging, you've imaged a companion, then you get another equation, and what you have here are now 3 equations and 3 unknowns. So in a case like this, you can actually get away with just solving 3 equations for 3 unknowns if you have a long orbital period and you happen to have these different sources of data. So I found that to be really, really cool. So the rest of my talk, or a large fraction of it, is going to consist of answering this question. What might stop us from actually doing all of this cool stuff? Can we just go and do it? And my answer is you have to check a bunch of things and do a lot of legwork first. So the goal here is to use these differences in proper motion to probe accelerations. The proper motions come from different sources. We're not necessarily sure that they're on the same reference frame. The Guy and Hipparcos teams worked very hard to get their reference frames nailed down, but they quote uncertainties in them because nobody can do it perfectly. It's not possible. And then, are the uncertainties appropriate for this? Gaia, if you go to its archive, it quotes the formal or the internal uncertainties needed to get a formally good fit to their sky paths. That may or may not be the uncertainty that we need to compare these different data sets. We need to check. We cannot just take those uncertainties as given. In order to do this, I'm going to run with the following hypothesis. Most of the stars that we can probe in the sky are not accelerating by very much. So I can use a large fraction of the stars in the sky to kind of baseline what these should look like. And for that large fraction of the stars, if I take the difference in proper motion on the top, and I divide by the uncertainty in that, we call that a z-score, and that should be drawn from a unit Gaussian, if everything is perfect. Gaussian because everything's Gaussian, hopefully, central limit theorem, and a unit Gaussian because we want that uncertainty to reflect the actual standard deviation of the distribution that produced these differences. So in order to use these, to be able to trust whether we have significant accelerations and use them for orbit fitting, we need to check. And if you just go and check, then you find that it doesn't check out if you just download the catalogs as they are published. It's not surprising, but it's work to do to understand it better. So that dashed line here, the black one, is a unit Gaussian. And none of those histograms match the unit Gaussian for these proper motion differences normalized by their uncertainties for nearby stars. It's especially bad in this case for the bright stars, G less than 6. So if your z-scores are too broad, it probably means your denominator is too small. Your errors are underestimated. If you want to tighten that up, you probably want to inflate your errors. And it looks like more error inflation is needed for the bright stars. I believe this is the Hipparcos re-reduction that I'm showing here, the 2007 reduction. Gaia eDR3, much the same thing. So the uncertainties as published are internal uncertainties, but they're not what we need for this. So that means that our next step is to actually go through the whole cross-calibration to produce something that you can use for these sorts of analyses. There are a number of subtleties. I'm not going to go through all of them here. I want to mention a couple of them, though. One of them is that because these are fits to sky paths, if you know part of that sky path, you can do a better job of fitting the rest. If Gaia, for example, tells you what the parallax is, then you can go and reanalyze the Hipparcos data and get a better answer for the other parameters like position and proper motion. Another subtlety is that because, again, these are fits to a sky path, the position at which you best, the time at which you best know the star's position will vary from one star to the next. There's nothing magic about 2016.0 for DR3 or 1991.25 for Hipparcos. Those are typical numbers, but the epoch of best measured position does vary a little bit. And so we do our best to take that into account. Another nuance with Hipparcos that really surprised me when I was getting into this is that many of you might know there are two reductions of the raw data. There's the first one, which is itself a combination of two reductions, a merger of two reductions put out in 1997. Then there was a re-reduction with a heroic amount of effort released in 2007. So which is best? Traditionally, people use the second one, which quotes much smaller uncertainties and seems better. But the answer that really surprised me is that the answer is both. Your best answer is a mix. If you just mix up the two Hipparcos reductions, you do better at enormous significance in either one on its own. So we have this hierarchy where the mixture is better than just Hipparcos 2 is better than just Hipparcos 1. My hypothesis for why this is that each reduction made its own assumptions, its own different errors, and some of those were correlated, some of them were different. And if you combine things together, then you can beat down those uncorrelated errors. So Hipparcos 2 does not strictly supersede Hipparcos 1, but in fact complements it. To convince you that that's the case, all I'm doing here is taking the difference in proper motions between Hipparcos and the long-term proper motion, where I'm using different Hipparcos reductions to do this. The red line is if I just use Hipparcos 1, the original 97 reduction, and take the Hipparcos proper motions minus the long-term ones. If I take the Hipparcos 2 proper motions, I get a tighter distribution. And if I mix them up, I get an even tighter distribution. So a mixture of the two Hipparcos reductions outperforms either one on its own. And holding the uncertainties fixed, I can actually assign a significance to that of about 150 sigma. So it's enormously significant. And so that's what I ended up doing, is just taking the 60-40 mix. To show you how some of the corrections to the proper motions themselves come in, I'll show you a correction for an example field in DR2. There are a number of little subtle things here, and these corrections are going to be smaller in DR3. All kinds of subtleties with the frame rotation and at different magnitudes in DR2. They remain present to some degree in DR3, but there was a correction that was applied to the bright stars. So this is all stuff that is hidden from you if you use the catalog that I'm discussing, the Hipparcos Sky Acceleration Catalog, but it's present under the hood in the construction of the catalog. In DR2, if I take the differences of the Gaia proper motions with the long-term proper motions and just plot them for a whole bunch of stars, you can maybe see that things seem to be going up and to the right. It seems unlikely that the whole field would be accelerating up and to the right in this case. And indeed, this is interpreted as a frame rotation. The fact that Gaia in this case was unable to perfectly realize the reference frame that it was targeting. If I correct for that reference frame based on the global best fit, and Gaia does provide this prescription for DR2, you might notice on the top, this little histogram up there, things still look a little bit off. Well, we can maybe do a little bit better. Okay, so then back to the uncertainties. In order to calibrate these and make sure that they're reliable for identifying accelerating systems and fitting orbits, I did different things for Hipparcos and for Gaia. For Hipparcos, Gaia, for all intents and purposes, tells you which stars aren't accelerating. It defines that sample for you because Gaia is so much better at measuring proper motions than Hipparcos is, well over a factor of 10. And so this lets me define a sample and measure the error inflation that is necessary for Hipparcos. It's pretty substantial for the bright stars, especially relative to Hipparcos 2. For Gaia, we don't have that reference of a much more precise data set where it tells you which stars are not accelerating. So what I did was I turned, in this case, to the decades-long precision radial velocity monitoring to give me a clue. Radial velocity measures acceleration along the line of sight in an inertial reference frame. So my hypothesis for this is that if a star isn't accelerating along the line of sight, it probably isn't accelerating this way either. You would need quite the fortuitous alignment. So the purity should be much, much higher if you pick a sample. In this case, I was able to get almost 1,000 stars defined by a lack of radial velocity acceleration at a precision significantly exceeding Gaia's. And from that data set, I determined that the eDR3 uncertainties needed to be inflated by about 35–40% to bring them into formal consistency. This is smaller than the uncertainty inflation that I needed for DR2 and reflects, I think, a remarkable improvement in the quality of eDR3 relative to DR2. I'm saying eDR3 in many cases here. For the proper motions that I'm using in this case, eDR3 and DR3 are interchangeable. DR3 has a whole bunch more cool stuff, like the stuff that Alessandro talked about, but if you're just talking about the 5-parameter astrometric fits, it's the same for almost all stars. The parallaxes proper motions may be revised if you have something in the non-single star fit, but for the vast majority of stars, they're identical. So this is showing, again, your standard normal distribution in this dashed line. And it's showing, again, these same z-scores. Our target is that they should match that dashed line for all of these stars that aren't accelerating radially along the line of sight. And this is with the formal Gaia uncertainties. You can see that it's not too bad, but there's a little bit of a tail at high and low ends. There are too many 4 and 5 sigma outliers and too many 2 to 3 sigma ones too, but not egregiously so. If you apply this error inflation, then it looks basically perfect to my eye. And statistically, these are indistinguishable. And so this, again, is thanks to decades of monitoring by these teams and the openness in releasing their data so that I can actually go and check their radial velocities. So it's only thanks to the openness of the data teams of both Gaia and the RV teams that this kind of work is possible. At the end, we get a typical acceleration precision that is remarkably good. Something like 5 microarc seconds per year squared. So here, this is plotting the median residual in microarc seconds per year. So this is a proper motion difference. To get the precision, you would need to then divide by the time baseline. And then there's a little median versus mean conversion. Don't worry too much about that. But this precision is just amazing. And it's a big factor improved using DR3 instead of DR2. The improvement from DR3 over DR2, especially for the bright stars, has been something like a factor of 3 to 4. And so our sensitivity to astrometric acceleration was good with DR2, but it improved with this orange line by something like a factor of 3. This is about a third. And for many stars, we are now limited not by Gaia's precision in proper motion, but by Hipparcos' precision in measuring a position 30 years ago. Potentially, by measuring positions in the future, we'll be able to do even better and remove Hipparcos as a necessary constraint on some of these fits. So this whole procedure produces what I call the catalog of accelerations, even though it's really a catalog of proper motions. You can subtract them and get accelerations. And so the goal is to use these as appropriate quantities for finding accelerators and for fitting orbits. A couple of notes of caution that I think I've already said, so I don't need to repeat them. Okay. And just to show you that indeed these do look pretty good, these are the final Hipparcos residuals. There is some tail at large z-scores, but I haven't filtered out the real accelerators here. So many of these tails at high significance proper motion differences Many of these are real accelerators. In the core of the distribution, it looks pretty accurately Gaussian. Gaia looks accurately Gaussian in the core, but in this case, there are so many accelerators that instead of drawing a unit Gaussian to guide your eye, I'm guiding your eye with a mixture of a unit Gaussian and some kind of ad hoc broader distribution. So this, again, guide your eye distribution has about 30% of the sample that's actually accelerating. And that number, 30%, roughly matches what you get if you do a formal statistical check. So lots and lots of real accelerators in this system, mostly stellar binaries. I don't want to do too much of this, but these are things that we've developed at UC Santa Barbara, some of which will show up in the hands-on session. So Orvara will show up in the hands-on session. And though it doesn't show up directly, the 100,000 orbit fitter, which Mirek wrote, will be in there because Orvara uses it as a dependency. And if you want to understand all of the vagaries about Hipparcos and Hipparcos data reduction, then go talk to Mirek because he's doing heroic work on that now. So what this means is that we can fit orbits with Gaia today as long as we have some other data to help us. If we just have 3 proper motions, we're not going to fit an orbit to those. But if we have those 3 proper motions in an inertial reference frame, and we have RVs, and we have relative astrometry, then we're in very good shape. And that's what you'll be playing with. So one application of this is to discover new companions by looking around stars that are indeed accelerating. That acceleration constrains m over r squared, and so you always have an ambiguity when you look at these things. It could be a star that's widely separated or a planet that's nearby. You don't know. And so if you go and you look at all these accelerating stars, you're going to find a mixture of these things, but most of them will tend to be these wide stellar companions. If you also have precision RVs, then you can do a whole bunch of cool stuff. I want to advertise specifically Pierre Carvella's talk for that. And this other work, I'm not citing every author who's been doing this. I apologize. I did my best to cite a representative sample where you can use the combination of precision radial velocities and absolute astrometry to constrain the mass, orbit, and inclination of a radial velocity detected exoplanet. And some of these people are here at the conference today or at the workshop today. So go and ask them. For direct imaging, we can take some of these stars that are astrometrically accelerating and go take a picture of them. So here are 2 results from posters today. There are other posters, specifically call out Mariangela Bonavitas, using the same idea, using these stars that are accelerating to find new planets and brown dwarfs. And so if you want more information on any of these, go talk to these people and their posters. Mirek's talk tomorrow will also have a lot of this information. So please go and speak to all these people about the cool stuff that they can do. Again, I'm not presenting the results here because they're going to be in Mirek's talk and they're in all these other posters. So I encourage you to go and find it from the source. Okay. If we do have imaging, then we're in great shape because with imaging, usually we would be in the situation where we would measure a brightness and you try to guess the mass based on your understanding of the system age, based on your understanding of how planets and brown dwarfs cool. Now we can fit an orbit, we can get the mass. And so rather than using our data to try to figure out what the mass is, we can know the mass and use our data to try to understand the physical nature of what it is that we've found. To give you an idea of what the current significance is of some of these objects in the eDR3 catalog, I put sigmas on a bunch of these things. So for beta pic, the current significance of the astrometric acceleration is 3 sigma. So absolute astrometry itself can help you get a mass. Ignaz Snellen and Anthony Brown did the first work on that. It doesn't give you that precise a mass yet. And part of the problem is that beta pic's actually too bright for Gaia. So Gaia struggles with a star that saturates it that badly. HR8799, if you've been at all paying attention to the direct imaging community, you have most certainly seen pictures of this star. and its planetary system because it's maybe the most photogenic one, and so it's the one everybody shows. There's now a 5 sigma, roughly, measurement of its acceleration, and so that can give you a mass of the closest planet in the system. 51 Eridani is another directly imaged planet. It's pretty low mass. The significance there is 0 sigma, so consistent with no acceleration. And Pi Mense, I checked that one, it's about 8 sigma. If we go to more massive companions, then the sigmas go up by a lot. So those are all well-known directly imaged brown dwarfs on the right-hand side, and the top couple are tens of sigma. In the case of Gliese 229 and HR 7672, over 100 sigma. And so for some of these, you can get masses that can be precise to about 1%, even though the periods are very long. And Mirek's talk will go through those in a lot more detail. So as you go from the left-hand side to the right-hand side, the masses of the companions go up by a factor of several, 5 to 10 often, and the significances go up correspondingly. So right now, this sort of technique can help you find planets and brown dwarfs. It gives you really good mass measurements of brown dwarfs, white dwarfs, and very low mass stars. I wanted to just make one quick comment on proper motions as plotted by Orvara before I wrap up. This is relevant to the hands-on session, and again, it's yet another form of the caution that I've given you a couple of times about the fact that it's not proper motions that are being measured, but proper motions are being fit to sky paths. So Orvara by default plots these proper motions, and you see a point. Here's the proper motion that Hipparchos measured. Here's the proper motion that Gaia measured. You don't see that long-term proper motion plotted here. What it actually is an integral constraint. So the area under all of these orbits is somehow magically the same, and that happens to be enforced by this measurement not plotted of the long-term proper motion. Strictly speaking, even these points here come from integrating this curve, albeit over a much smaller region. And so where you see this discrepancy that looks by eye to be 10 sigma or something egregious, you can't necessarily trust that. Orvara will actually spit out what the chi-squared is corresponding to that best orbit, which comes from computing that integral constraint. And in this case, I don't remember what it is, but the chi-squared is low. So this is a formally good fit, even if this plot arguably doesn't show it most effectively. That would be something that you guys could also think about, is how exactly should we be visualizing these integral constraints in a way that's intuitive and reflects the fact that if you go and you look at Gaia, what you actually see in the catalog is a proper motion. Okay. Towards the future, this is kind of foreshadowing some things that will be discussed on Friday. This talk has been about how you can do better with Gaia by leveraging a position measurement far in the past. Someone in the future could do the same thing by leveraging Gaia with another very, very precise position sometime in the future. I'll specifically call out Scott Gowdy's talk on the Roman Space Telescope and astrometry with it as a candidate for how you could extend the astrometry way into the future and be sensitive to companions at lower mass on very wide separations. So here, these separations where you have this additional measurement, it really fills in these tens of AU separations, the Uranus-Neptune type separations that could then be imaged with big telescopes from the ground, or objects like this at tens of AU, very, very cold, would be excellent targets for something like Webb. I don't think the timing will work out. I mean, if you're talking about something maybe in 2030, Webb's not going to be looking at them then. But these at very, very wide separations would be extremely good candidates for an infrared observatory. So I want to leave you with that, kind of a preview of the future talks on results that will be coming tomorrow, and a little bit of background on what it is we need to do in order to use Hipparchos and Gaia to identify accelerating systems, and fit orbits. And then in the hands-on session, if you choose to do the Avara one, you'll actually get some practice with this. There are going to be big sensitivity improvements coming with future data releases, and I look forward, I suppose, to the calibration problems that those may present. Although, as Gaia continues to do amazing work, then I'm guessing there will be less of those. The intermediate astrometric data may present their own hurdles, though. So with that, thank you.
Some questions in the audience here, and then we'll go online.
May I start? Tim, you've done a great job in getting to grips with two very complex data sets.
Thank you.
Can I make 3 comments?
Of course.
In my defense of Hipparchos?
I didn't mean to attack your Hipparchos. I'm terribly sorry.
And you didn't. But let me make a couple of points. The first is that, exactly as you said, the solution published in 1997 was the combination, a very careful combination of 2 independent reductions. And those independent reductions were, they both had their own random errors because of the way the equations were formulated, and their own systematic contributions because of the way the measurements were actually made. We were very, very clear in 1997 that you could do better by continuing to iterate this solution, for example, including the chromatic aberrations and so on, and going back and iterating. But there is, and I think this is an important lesson for, or an important message for Gaia as well, there has to be some compromise between the point at which you stop the iterations or the adjustments and the point at which you put out some sort of definitive catalog. Astrometry had a very bad reputation in the mid-1900s because a lot of catalog production work took decades before it was released to the community. So we took a very specific decision to release something in 1997 with all its blemishes and so on. So that will be a problem for DR5. I think Anthony is well aware of this, that at some point you will say, right, this is the end of our reduction, but there will always be, the Gaia solution is a massive iterative adjustment of all kinds of things there. And you will always do better in the future. And you have to decide as a community whether you want to draw the line under it and say, this is a definitive solution, or whether you want to continue producing updates that the community can frankly be at a great loss as to how they really reduce that.
I actually have a question.
No, can I finish my comments?
Yes, and I'll ask you a question.
No,
Yes.
because I mean, you understood that very, very well. And I just wanted, it's a comment really for the future. The second is that you identified and underestimated the Hipparchos errors. And again, let me be rather clear there that these were formal standard errors that resulted from the least squares adjustment. And from various comparisons, we estimated that there was a 20% underestimate between the formal standard errors and the true external errors. So I don't know whether you took that into account, but it's worth commenting on. And it reflects back to a question that was made yesterday. Someone asked, why are these reduced unit weight errors? Why do you get things significantly less than unity? And you get this because in any measurement system, exactly as Anthony said, you've got a range of standard errors. And that's exactly why, for example, Hipparchos has negative parallaxes, and it's why Gaia will have negative parallaxes. You can look at this catalog and say, how the hell can you end up with a negative parallax? Because that's unphysical. But in any system of proper measurement errors, they will appear because of their errors. And I wanted to make one final comment, and I might have missed it. You talked about these 3 proper motions, but Hipparchos also published the full covariance matrix for all the solutions, and also the 7 and 9 parameter solutions, which would give a hint as to the acceleration terms. Yes. And I probably missed it, but did you take those into account in your reductions?
We did take the covariance matrices into account. So when you propagate to the epoch of minimum uncertainty, you basically get rid of the covariance between position and proper motion. We use the Gaia parallax to constrain post facto the Hipparchos fit, again, using the covariance matrix. And then you're left with covariances between RA index position, RA index proper motion. Those are carried on into the catalog of accelerations. We did not tackle the 7 and 9 parameter fits we will be looking at those together with the Gaia 7 and 9 parameter fits and seeing if for various sources, the Hipparcos and Gaia 7 and 9 parameter fits and the long-term proper motion anomalies tell consistent stories. Thank you. And actually, a question for maybe you and Anthony, to reverse the usual questions. Is there any possibility or thought that some of the sources in Gaia might be held back from the iterative solution, as in not used to construct the iterative solution in order to serve as a future, the word just slipped out of my mind, cross-validation data set?
Yeah, that's a good suggestion. I don't think we have considered that. It is true that we don't use all the stars in the iterative solution. Only a subset that we consider are probably not binaries, etc. We have done for the first data release a little bit of that, where we looked at the solutions for subsets of the data. But yeah, I don't think there are any plans in that direction, but it's a good suggestion. Yeah.
Hi, David Hobbs from Lund. I think this is a dangerous business, what you're doing here. And if you look back at what happened with Gaia data release 1, there we used Hipparcos data to do the T-gas solution.
Yes.
And that made a lot of sense because we had very few observations, and
Yes.
then we could get proper motions and so on.
Yes.
But from then on, the Hipparcos data was dropped. And the reason is that the difference in the accuracy of the measurements, Hipparcos is about a factor of 100 worse than Gaia. And basically, we found that Gaia itself on its own was able to give more accurate results. So I worry that when you include Hipparcos data, what you're doing is also risking bringing in systematic errors from Hipparcos that aren't in the formal errors as well. But one way you could check this is if you look at DR3 now, we have acceleration solutions.
Yes.
So have you compared with those?
We're starting to, and An has a poster, Shiran has a poster starting to do exactly this and compare the orbits that we get from these long-term proper motions or proper motion anomalies with the internal accelerations given in DR3. And there are a handful where we can check.
Yeah.
And so you can discuss with her about what she is starting to find. I will also say here that the catalog publishes or carries over Gaia DR3 or eDR3 exactly as is and supplements it with these 2 additional proper motion measurements, a long-term proper motion transformed onto the Gaia DR3 frame and the Hipparcos proper motion. And so to see whether or not these are sensible quantities and the uncertainties are okay, that's this whole business, for example, of this cross-validation set where I held it back from all of the previous analyses to check about whether the long-term proper motions and the Gaia proper motions were consistent with one another.
Okay. Yeah. Yeah. Okay. So anyway, I have this caveat, but I think for the future also, I think we should be very careful about this combining data sets, and it's something that we all want to do in the future because we have these wonderful new missions. But we have to be very careful that we take into account the difference in the accuracy of the different measurements.
Oh yes.
Because if it's not done properly, it would give very misleading results.
Oh yes, and most of these, so if we look here, then these are the calibrated uncertainties in the Gaia proper motions. And then these are the uncertainties in the long-term proper motion, overwhelmingly dominated by Hipparcos uncertainties. So yes, the long-term proper motions have uncertainties that basically come from Hipparcos. Gaia makes a negligible contribution to almost all of them. And then the Gaia motions and their uncertainties are carried through.
Okay, thanks. I'll look at the post.
So let's take one question online.
Yeah, so we have a question online. Have you compared what you call Z-score to the T distribution, which is broader at the base?
No, I have not. In this case, I'm comparing some enormous number of measurements. or I have an enormous catalog, and so I have such a large quantity of objects that the assumption that it's just a unit Gaussian is pretty good. If you have 100,000 stars or something, then a 3-parameter here and there doesn't mean very much. These are the results of astrometric fits. And so if you want to then dive down and look at the epoch astrometry at the fits internally within Gaia, then you have to be a little bit careful. But in this case, with the results of those fits, I think I'm safe.
Okay, I think that's it. We're going to go into our lunch break and give Tim some time to work on the inertial reference frame dance. Oh, not lunch break. I'm not hungry. Coffee break. And you'll have time to work on the inertial reference frame dance. So, all right, let's thank Tim again.